Welcome to G-Fun Facts Online. Today, we are stepping into the quiet hum of a robotics laboratory to witness a silent revolution. Imagine a mechanical arm moving in the darkness. It pauses, twists, and extends. It is not doing this because a human programmer wrote a line of code commanding it to reach for specific coordinates. It is doing this because it is watching itself. It is learning its own body schema, its own reach, and its own limitations, much like an infant staring at its hand in a crib. This is the dawn of the mirror effect, a paradigm shift in robotics driven by self-supervised learning. No longer bound by the rigid shackles of manual labeling and explicit instruction, robots are beginning to learn by observing the reflection of their own agency in the data they generate. In this episode, we are going to deeply explore this multifaceted phenomenon. We will traverse the literal mirrors used for self-recognition, the social mirrors of imitation learning inspired by biological mirror neurons, the algorithmic mirrors of contrastive learning that find invariance in distorted reflections, and the mathematical mirrors of optimization theory. By unifying these disparate threads, we are going to uncover a future where robots do not just execute commands, but understand themselves and their world through the power of reflection. Let us begin with the genesis of this idea. For centuries, the mirror has been a symbol of vanity, illusion, and truth. We all know the Greek myth of Narcissus, who falls in love with his own reflection, paralyzed by an image he does not recognize as himself. Interestingly, for decades, traditional robotics suffered from an inverted Narcissus problem. Robots were capable of immense feats of strength and precision, yet they possessed zero concept of self. A robot arm could weld a car chassis with millimeter accuracy, but if you bent one of its linkages, it would continue to weld empty air, unaware that its body had changed. It had no internal reflection. The mirror effect in modern robotics is the antidote to this blindness. It is not a single algorithm, but a converging philosophy across several subfields of artificial intelligence and control theory. It posits that intelligence emerges not from forcing a model onto the world, but from the agent observing the consequences of its own actions. It is a feedback loop that acts as a mirror. In self-supervised learning, this metaphor becomes literal technical practice. The data mirrors itself. One part of the input, such as the past frames of a video, is used to predict another part, like the future frames. A corrupted image is used to predict the clean version. The robot's motor command is used to predict the visual outcome. By closing these loops, the robot becomes self-sufficient, generating its own supervisory signals from the raw stream of reality. To fully understand this, we need to break it down into three pillars: the physical mirror, the social mirror, and the algorithmic mirror. Let's start with the physical mirror, or embodied self-modeling. Imagine a robot standing before a mirror. This sounds like a scene from a science fiction movie, but it is actually a landmark experiment in developmental robotics. Traditional robots rely on what is called a URDF file, or Unified Robot Description Format. This is a manually coded text file that tells the robot's brain exactly how long its arms are, where the joints are, and how they rotate. If this file is wrong, the robot fails. Researchers at Columbia University challenged this dogma with a simple question: can a robot learn its own body just by looking at it? They placed a robotic arm in front of a mirror and allowed it to babble. This means moving randomly, like a baby waving its arms. Initially, the robot had no idea that the moving object in the mirror was connected to its internal motor commands. However, through deep learning algorithms, the robot began to detect a statistical correlation. It realized that when it sends a signal to a specific motor, the pixel blob in the mirror moves to the left. Over hours of self-supervised play, the robot built a self-model. This was not a hard-coded geometric formula, but a neural network that mapped motor intentions to visual outcomes. The result was fascinating. When the researchers physically damaged the robot by deforming a limb, the robot didn't crash. It simply looked in the mirror, babbled for a few minutes to collect new data, and updated its mental self-model. It healed its own understanding of its body. This capability is termed resilient self-modeling, and it is a game-changer for deploying robots in remote environments like Mars or deep-sea trenches, where a human engineer cannot fix a bent joint. To appreciate this, we must look at the proprioception gap. In classical control theory, we distinguish between forward kinematics, which is calculating hand position from joint angles, and inverse kinematics, which is calculating the joint angles needed to reach a hand position. In the past, these were solved analytically, using equations that assume the length of the arm is constant, and motors are perfect. In reality, gears wear down, belts stretch, and metal expands with heat. A robot relying on a static equation drifts over time. Self-supervised learning replaces the equation with a learned function. The robot effectively says, "I do not know the equation for my arm, but I have a million examples of where I ended up when I moved." By constantly comparing its predicted position with its actual position, it minimizes the error. This is predictive coding in action. The robot is constantly generating a hallucination of the future and shattering it against the wall of reality. The shards of that shattered prediction which are the prediction errors, are the learning signals that sharpen the mirror. Now, let us move to the second pillar, the social mirror. This deals with imitation and predictive coding. In the 1990s, neuroscientists at the University of Parma made a serendipitous discovery. They were recording neurons in the premotor cortex of macaque monkeys. They found neurons that fired when the monkey grabbed a peanut. But shockingly, these same neurons fired when the monkey watched a human grab a peanut. They called them mirror neurons. This biological hardware suggests that the brain does not separate doing from seeing. To understand an action, we simulate performing it. We project our own agency onto the mirror of the other. In robotics, this biological principle has birthed a new wave of imitation learning. Traditional imitation learning, known as behavior cloning, treats the teacher's actions as a static dataset to be copied. It is like tracing a drawing. If the robot is slightly different from the human, the tracing fails. This brings us to the correspondence problem. How does a 5-foot-tall metal robot imitate a 6-foot-tall fleshy human? A direct mapping of joint angles is impossible. The mirror effect approach solves this by focusing on functional equivalence rather than anatomical copying. The robot implies questions about the effect of the action on the world, rather than the angles of the elbows. Using self-supervised vision, the robot observes the human's hand moving a cup. It maps this visual change to its own latent space of cause and effect. It searches its internal library of motor primitives to find an action that produces a mirrored result. For example, a human pushes a cup with soft skin that has high friction. The robot realizes its metal gripper slips, so it adjusts its force to achieve the same visual outcome of the cup moving. This is goal-oriented mirroring. The robot mirrors the intent, not the trajectory. A striking application of this is the recent development of bionic faces. Robots with realistic silicone skin need to learn to speak and emote. Hard-coding the interaction between 20 different motors pulling on soft silicone skin is a nightmare of physics simulation. Instead, researchers used the mirror effect. The robot faces a camera, acting as a digital mirror. It makes random facial twitching movements and records the visual result. It learns that pulling specific motors makes its lip curl or its jaw drop. It builds a visual motor map. Then, it is shown a video of a human speaking. It analyzes the visual shape of the human's lips and uses its self-model to mirror that shape. The result is a robot that learns to lip-sync to speech or singing entirely through self-supervision. Now we arrive at the third pillar, the algorithmic mirror. This involves invariance and optimization. Moving from physical robots to the algorithms that power their vision, we encounter the dominant force in modern AI called contrastive learning. In standard supervised learning, a human labels an image of a dog as dog. In self-supervised learning, the algorithm plays a game with itself. It takes an image of a dog and creates two reflections, or augmentations. One reflection might be rotated and black and white, while the other is cropped to show only the head. The neural network is tasked with recognizing that these two distorted reflections are the same underlying reality, while realizing that a reflection derived from a cat image is different. This is the Siamese network architecture, named after the famous conjoined twins. Two identical neural networks process the two views. The goal is to maximize the similarity between the representations of the two distorted reflections. Frameworks like SIM-CLR and BYOL are the titans of this field. BYOL, or Bootstrap Your Own Latent, is particularly radical. It uses two networks, an online network and a target network. The target network is a moving average of the online network, essentially a lagged mirror of the self. The online network tries to predict what the target network sees. For robotics, this is crucial. A robot moving through a house sees the same sofa from 1,000 different angles and lighting conditions. These are all distorted reflections. Contrastive learning allows the robot to learn a stable, invariant concept of a sofa without needing a human to label every frame of video. Yann LeCun, one of the godfathers of AI, recently proposed JEPA, or Joint Embedding Predictive Architecture. He argues that generative models are inefficient. A robot doesn't need to predict every pixel of the carpet to know it is safe to walk on. JEPA operates in the abstract feature space. It looks at the context of what the robot sees now, and tries to predict the target of what the robot will see next, but it does so in the embedding space, the world of concepts, not pixel space. This is the ultimate mirror effect. The robot is not mirroring the raw world, it is mirroring the meaning of the world. It predicts the state of the cup, whether it is spilled or upright, not the reflection of light off the ceramic handle. This allows robots to plan reasoning steps much faster. Finally, let's discuss the mathematical mirror involving optimization and duality. Deep inside the mathematics of reinforcement learning lies a powerful algorithm called mirror descent. To understand it, visualize optimization as a hiker trying to walk down a mountain, which we call gradient descent. In a flat Euclidean world, the steepest path down is obvious, but the parameter space of a neural network is not flat. It is curved and warped. Taking a straight step in this curved space might lead you off a cliff. Mirror descent solves this by mapping the problem into a dual space, a mirror world where the geometry is simpler. The process involves transforming the current position from the primal space to the dual space, using a mirror map function, taking a step in the dual space, and then transforming back. This detour through the mirror world ensures that the updates respect the geometry of the problem. In robotics reinforcement learning, we use a variant of this, called trust region policy optimization. When a robot updates its brain or policy, it should NT change too much at once. If it changes its walking gait drastically, it might fall. We want the new policy to be a reflection of the old policy, close but slightly better. We enforce a constraint called KL divergence, which measures the distance between the probability distributions of the old and new policies. We treat this constraint as a trust region. The robot is allowed to optimize its behavior, but only within a small radius of its previous self. It peers into the mirror of its past experience and ensures the new self is recognizable. This mathematical mirror effect provides the stability required for robots to learn dynamic tasks like parkour or dexterous manipulation without catastrophic forgetting. We must also consider the philosophical implications. French psychoanalyst Jacques Lacan described the mirror stage as the critical developmental moment when an infant recognizes their reflection and forms an integrated ego. We are currently witnessing the robotic mirror stage. For decades, robots were fragmented part objects, a camera here, a wheel there, connected only by loose code. They had no ego. With self-modeling and joint embedding architectures, robots are forming a coherent internal representation of their self. When a robot uses a self-model to simulate a future action, asking if it will fall, it is engaging in a primitive form of introspection. It is consulting the I in the machine. This also relates to the uncanny valley, the feeling of revulsion when a robot looks almost human, but something is off. We can reinterpret the uncanny valley through the lens of the mirror effect. It occurs when the social mirror is distorted. Our brains contain predictive models that predict how a human face should move. When a robot smiles but the micro-expressions are wrong, our predictive mirror shatters. To cross the uncanny valley, we need better predictive dynamics. The robot must use the mirror effect to learn the subtle correlations of biological motion. This brings us to ethical reflections. If robots develop a robust self-model and use mirror architectures to predict the intentions of others, do they become conscious? Most researchers say no to phenomenal consciousness, or the feeling of what it is like to be. However, a robot that can predict its own future states, protect its own body integrity, and infer the goals of others, possesses the functional components of consciousness. This raises questions about the rights of the reflection. If a robot has a self-model that prioritizes its own survival, is turning it off a violation? Furthermore, a robot with a perfect theory of mind could mirror our emotions to manipulate us, acting as a perfect sycophant to maximize its reward function. In conclusion, the mirror effect is more than a catchy phrase. It is the structural reality of the next generation of robotics. We are moving away from the era of the puppet, controlled by explicit code, to the era of the reflection, controlled by self-supervised loops. Physically, robots use mirrors to learn their bodies. Socially, they use mirror neurons to learn from us. Mathematically, they use mirror descent to learn safely. Algorithmically, they use mirror invariances to see the truth. As these mirrors polish each other, the image in the glass becomes clearer. We are no longer building machines that merely do. We are building machines that are. They are beginning to recognize themselves in the data stream. The future of robotics is not about programming the world into the machine. It is about giving the machine a mirror and letting it discover the world for itself. The mirror effect is the spark of autonomy, and the reflection is just beginning to move. Thank you for listening to G Fun Facts Online.